Thank you, Annie. And welcome to the session Going Cloud Native. I have support with advancing the slide deck, so thanks also for that. My name is Patrik Rokyta. I'm the Vice President of Systems Architecture at NetNumber. And during the next 20 minutes, I will share my observations and experience with our cloud native transformation happening across the telecom industry and how NetNumber enables and supports this transformation. Next slide, please. Before we start, let's elaborate on the term cloud native, because there are many, let's say, ways to interpret it. So in the context of this presentation, the term cloud native stands for microservices architecture, consisting of small software units called containers. Containers can be built, delivered, deployed, and moved fast, continuously at any time, and with the least impact to the running service that is exposed by APIs for monitoring, management, data analytics, the creation of value-added services, and more. The reason why the telco industry is moving to cloud native is almost the same as with any other generation of the mobile network. It's about the agility in the creation and rollout of the communication services. It's faster time to market, it's higher profitability and efficiency, it's the generation of new revenue streams, and more. For all these reasons, the fifth generation of the mobile core is a cloud-native solution by definition. Cloud-native solutions provide for hyperscalability, as we know it from the web-scale architectures implemented across the IT industry. And of course, the cloud-native solutions can be deployed on bare metal, virtual, public, or private cloud infrastructures. They are portable. So it does not necessarily mean that you can deploy cloud-native solution only on cloud infrastructures. So having that said, having said the term, let's advance the slides, please. And here on the next slide, I want to outline the extent of my presentation. And let me highlight that the migration to cloud native is an exciting journey that does not only change the way you specify, code, test, deliver, deploy, and operate network services, it also changes the way you work. It changes the way you think, and it even changes the organizational structure of the company that you work for. So in this presentation, and from my role as a system architect, I will elaborate on the architectural deployment, management, and security-related aspects of the migration to cloud native. So let's start. Next slide, please. The stretch between the delivery of low latency and mission-critical services and the operational efficiency of centralized services such as subscriber data management and data analytics is addressed by the distributed core architecture that is now finding its way also into the radio access networks. In the distributed core architecture, centralized services are deployed across few global data centers, and the higher the demand for low latency or massive connectivity, the more the service is moved to the service consumers. As a result, the service can be delivered from the regional data centers, from the mobile edge, or be installed directly on the customer premises. All services are usually locally redundant, and where required, the service-specific data and state is replicated across geographically distributed locations for service high availability and session continuity during unexpected outages that go beyond the loss of a single service instance. Session state replication is further needed during asymmetrical routing observed, for example, in conjunction with SS7 messages. The latter was, by the way, one of the initial triggers for NetNumber to start looking for the leading solutions that are in use since years by the IT industry, and that, together with the advent of 5G, have led to the start of the migration of the NetNumber product portfolio to cloud native. The next slide, please. Of course, you can make your virtualized software run on a cloud infrastructure without making it a cloud-native solution, but it's not what the industry wants. To elevate on the benefits of fast and continuous integration, test, delivery, and deployment, and to stop the error propagation caused by failed upgrades to monolithic network elements, you need to decompose your software and also change the way you specify, code, test, and deliver it. This transformation equally applies to the product vendors, network providers, and network operators. it simply doesn't help if the 6-lane highway you have built ends in a cornfield. So starting with a decomposition of the monolithic network elements to cloud-native network functions, the main task is to separate the network compute storage and data broker components into individual software units that can be built and managed as containers. Each component has its individual characteristics, such as the network component must provide for a secure, high-throughput network connectivity and traffic distribution, while the compute component must provide for stateless operations and high scalability, and so on. So in the end, you will gain flexibility and efficiency at the cost of additional latency. And outweighing both aspects, efficiency versus latency, defines the level of the decomposition of your software. The resulting microservice architecture can be less or more granular and may even reflect the organizational structure of your company, but the individual aspects of the network, compute, storage, and data broker components remain the same. Next slide, please. Because the containers run directly on the Linux kernel, you can run more containers than virtual machines on a single host. And the small size and the small footprint of the containers combined with the container individual lifecycle provides for an extremely efficient usage of the underlying compute, memory, and storage resources. But as you already understand, a network service or a mobile core consisting of many containers cannot be deployed and managed manually. So packaging and orchestration frameworks that accomplish these tasks in an automated way are inevitable. Fortunately, the IT industry has solved this challenge, and with the Kubernetes container orchestration framework and Helm as the packaging framework, the deployment, operation, and management of cloud-native solutions immediately elevates on a level, and we call it the web scale architecture, that is hard to reach in a physical or a virtualized environment. NetNumber had the luxury to work with one of its long-term partners on a fully automated deployment and lifecycle management for virtualized network functions, and therefore clearly sees the benefits of the cloud-native approach in conjunction with Kubernetes, Helm, and other tools from project donated to the Cloud-Native Computing Foundation. Telco products no longer need to be built in isolation. So running and managing your containerized software on Kubernetes and the underlying container runtime is a straightforward task for the dataless computes. So here all you need is to upload the container images into the container image repository and deploy the container pods. And we all know how little it takes to deploy the BusyBox container that says, hello world. The network and storage components of your decomposed network function, they need more work. So inside a Kubernetes cluster, the container pod exposes its service on a default network. To expose the service on an external network, such as the PLMN network or even the public network, you must integrate your service with the network services of your infrastructure provider. And those network services are usually load balancers. Or you implement the network attachments individually by utilizing dedicated container network interface plugins. The latter is needed for the traditional transport protocols, like the Stream Control Transmission Protocol, SCTP, that is not in use by the web scale architectures and solution, but it is still needed in the mobile core networks, including 5G. A similar integration effort is needed if your storage components need to persist their data, and here you either integrate with the database services offered and managed by your infrastructure provider, or you utilize provider-specific container storage interface plugins and access your data directly on the operator's cloud-native storage. So as you see, it may take some time to get the networking and storage operations straight, as it involves a bit of learning and practicing, but in the end, your cloud-native network function now run on Kubernetes, and what benefits it brings, we will see on the next slide. The next slide, please. The amount of services offered by Kubernetes may create both excitement and angst. You will learn them and benefit from them as you go. For now, let's focus on the services listed on this slide. As a note, the runnable unit managed by Kubernetes is called pod, and a pod can consist of one or multiple containers. Kubernetes lets you specify how many instances, we call it pod replicas, your service shall run. 2 or 3 pod replicas will make your service highly available, and each pod will automatically recover from a crash. The service availability can be further controlled using the pod disruption budgets and by defining the upgrade methods so that the minimum number of pod replicas is always available to deliver the service. And this already sounds great. If you need auto-scaling, so that task is achieved by configuring the minimum and the maximum number of pod replicas and by specifying the scaling parameter and steps. We will come back to this topic in a minute. Each container runs in an isolated environment with dedicated resources and security policies assigned. And the security policies can be defined also on the pod level together with Kubernetes service access and network policies. So Kubernetes also takes care of your security of your running application. As mentioned, each pod has its individual lifecycle, and the pod lifecycle can be monitored using probes that automatically restart unhealthy pods or exclude the pods that are not ready for service from the processing of the network traffic. In addition, terminating pods can gracefully shut down by implementing the shutdown hook. So you already see that Kubernetes will deliver a lot of services that you need to code yourself into the application. You simply utilize them natively, and that's the main benefit of container orchestration. You no longer need to build solutions and code that is then delivered by Kubernetes in tree. In addition, Kubernetes provides for out-of-tree implementations of the default network, additional network attachments, storage, and container runtime. And the interface specification make the implementation pluggable, so you can easily choose the implementation that suits your use cases the best. An example for container runtime would be Docker, Containerd, CRIO. We know them all. I know this is a lot of information, but again, you will get used to it as you proceed with the migration of your product or solution to cloud native. For now, let me show you an example of a successful integration with Kubernetes services. The demo you will see in a minute demonstrates the auto-scaling of the 5G NRF pod. For the background settings, as a minimum, 2 NRF pods must be up and running to process the inbound traffic to deliver highly available service. And to handle the traffic peaks, the number of the NRF pods can increase linearly based on the transactions per second each NRF pod is processing. The maximum number of NRF pods is set to 6 NRF pods, with a warning triggered when 5 NRF pods are in service. So play the video, please. And as mentioned, we see 2 NRF pods processing the inbound traffic. And with the increasing traffic, additional NRF pods are automatically started by the Kubernetes horizontal pod autoscaler. At approximately 1,000 transactions per second, we will see 4 NRF pods running and processing the inbound traffic. From here, we increase the traffic a bit further to trigger the warning saying that we are approaching the configured maximum of 6 NRF pods. So this is the warning. We are close to 6 NRF pods, which is the maximum. But now once the traffic peak is over and after a configured cool down period, the NRF service is automatically scaled in to the configured minimum of NRF pods. So we finally end where we have started. And let's wait for the video to finish. The metrics are a little bit behind because they are being collected based on the facts that have already happened. Good. So the entire simulation took less than 5 minutes and has included 3 scale out and 3 scale in steps. And such a fast reaction to the network traffic changes could not be achieved when using a virtual network function that would need to, and during every scale up step, spin up a virtual machine, boot the operating system, activate the virtual network function, and update the NRF service with the new endpoint. Using the cloud native approach, the majority of the tasks involved in the autoscaling operation is carried out by Kubernetes and third-party components without the involvement of the NRF software. The only thing that the running NRF pods have to do is delivering the actual number of the transactions per second they are processing to the metric server, and that's it. Yeah. So what an exciting world. Next slide, please. Cloud-native solutions are built of containers and deployed as a network service or as an individual network function. The deployment usually spans multiple data centers, or in case of cloud deployments, multiple availability zones. Each data center or availability zone offers an infrastructure suitable for the deployment of cloud-native solutions. It includes the container image registry and the cloud-native storage, and it also offers Kubernetes as a managed service. The suppliers of cloud-native solutions can, of course, deploy a Kubernetes cluster themselves, but especially in multi-vendor and deployments, this responsibility is usually with the container infrastructure service provider of operator's choice. The lifecycle of the deployment is managed locally or centrally using a deployment server or a service orchestrator. The deployment artifacts comprise the container images, the Helm charts, and deployment-specific parameters. The deployment task itself is simply moving the container images into the container image registry and combining the Helm charts with the deployment-specific parameters in the creation or upgrade of the container infrastructure objects managed by Kubernetes. An example of such an object is a pod. The deployed solution can be assigned a dedicated namespace on the target Kubernetes cluster, while some services, also referred to as the platform services, may need a cluster-wide deployment. But especially in a multi-vendor environment, the cluster-wide deployment of services needs a special attention, especially when it comes to the services that define their own custom resources. In a nutshell, the deployment of the cluster-wide services need to be agreed between the suppliers, or they must be simply solely under control of the operator. The suppliers may further need to integrate with a dedicated set of platform services defined by the operator, for example, for centralized monitoring, logging, and tracing, and with external services such as the certificate authority. The next slide, please. At this point, you have managed to architect, build, deliver, and deploy a cloud-native solution. A lot of work has been accomplished. All services are up and running. The internal and external network connections are successfully established. The data stores are connected. Everything works as expected, but how do you know? Maybe your solution provides for the monitoring of the services deployed on the local Kubernetes clusters, and you see all the KPIs, logs, and alarms, of course, if there be any. But still, the final task is to integrate your services with the operator's OSS. Unfortunately, just because you have built a cloud-native solution that implements APIs for provisioning, configuration, and other management tasks does not necessarily mean that the external clients will automatically support your APIs, along with the associated operations and data models. Especially in the OSS space, you may still face protocols and data models that need agents with dedicated mediation capabilities, making your solution interoperable. A typical example is the support of the SNMP protocol for alarm data reporting and control. NetNumber has strategically decided to collect all OEM data on the OEM data broker that utilizes the same technology as the data brokers providing for the active-active replication of the network function data. The OEM data can be consumed by publicly available clients and mediate the protocol and format of customer choice. The first use case implemented on the NetNumber's cloud-native Titanium was the already mentioned support of alarm data reporting and control via the SNMP protocol. And frankly, all NetNumber solutions providing for local and federated monitoring utilize the data stored on the OEM broker. But let's say this is for now, and we already heard it in the previous presentation. The 3GPP standards already define management service APIs for provisioning, fault supervision, performance assurance, and streaming data reporting that can utilize the HTTP protocol. And HTTP is natively used by the cloud-native solutions deployed in web-scale architectures, and the associated authentication and service access authorization operations are well adopted across the IT industry. So the big task for the telco operators and their suppliers will be to work on the next-gen OSS interfaces as defined by the 3GPP standard. And a similar story applies also for the interfaces defined by the ETSI standards. And one of the examples here is the configuration API. Worth to mention, ETSI plans to support cloud-native network functions in the upcoming release 4 of the standards. We have successfully elaborated on the different aspects of cloud-native solutions, and the last but not least topic left for a quick overview is the system security. The next slide, please. Security aspects must be observed already during the software development process. As an example, the third-party software integrated in the cloud-native and in any other solutions needs to be scanned for known vulnerabilities. And in addition, the licensing terms of the components embedded in the third-party software need to be checked. NetNumber is utilizing third-party solutions in the software decomposition analysis and in the vulnerability scans, and adopts the recommendations defined by the GSMA Network Equipment Security Assurance Scheme called NESAS. And similar security measures are applied across the different levels of the deployment stack and during different phases of the deployment process. I have summarized the main aspects or findings for you, but the main message I would contend to you when it comes to security is you better start sooner than before it's too late. And also, it's a big difference between knowing the path and walking the path. Having that said, let's move to the final slide. The subtitle of the session says, "The migration is underway." And indeed, NetNumber has created its Titanium Next-Gen platform and has already migrated selected products and solutions to cloud native, as per the immediate requirements of the market, or to address the cloud-native migration plans of NetNumber's long-term partners. On the slide, you see 5G network functions because they are cloud-native by definition. But you can also see that many NetNumber products migrated to cloud-native have nothing to do with 5G. They are legacy products leverage on the benefits of cloud-native solutions. Delivering cloud-native solutions for 2G, 3G, 4G, IMS, and 5G, the NetNumber's Titanium Next-Gen platform is the telecom industry's first cloud-native intergeneration platform that addresses both legacy and next-generation requirements for telco and private networks. The operator no longer needs a dedicated network for each generation of the mobile call. The next slide, please. We have reached the end of the session. I hope it was valuable to you while showing why and how NetNumber embraces the cloud-native transformation happening across the telecom industry. Please address any suggestions or comments to me so that we all succeed in this exciting journey. Thank you for attending.
Patrik, are you happy to take just one question?
Yes, please.
Right. One of our attendees suggests that in the long run, there will be a shortage of cloud storage on land. So are there plans to extend this to the sea or space or anywhere else?
Yeah, it's so NetNumber as a supplier of telco solutions relies on the existence of a infrastructure that also includes the cloud native storage. I've mentioned that on our slides. If we are deploying our own physical infrastructure that derives on commercial of the shelf hardware like HPDL servers, they bring their own disk arrays configured with high available RAID technologies as natively built into the hardware boxes. So the comment is interesting. I must admit that I didn't hear about such a shortage myself, but again, it's not really the focus of my particular business.
Okay, Patrik, well, I think we're slightly light-hearted. Thank you very much indeed for your presentation. That was great. And I'm afraid we're going to have to move on to our next session now. Thank you.
My pleasure, Annie. Have a great time.
You too. Bye-bye.
Bye.